Hi students, today we are going to be doing the second half of the chapter 7 topic, and we will pick right up where we left off with the first part 1 video for chapter 7. All right, so part 1 was left off with us having laid the groundwork that light acts as a wave. And we know that based on the interference pattern that is observed when you have light passing through a barrier with two slits. So that was where we left off. Now we want to transition into understanding why people say that light sometimes is not best described as a wave, but instead as a particle, which we now call photons. So let's get into that. All right, so start off with the statement. In some cases, light is best, which is we call electromagnetic radiation. Light is best described not as a wave. Okay, so a wave would be, where you've got both amplitude and wavelength, all right? But sometimes it's best described not as a wave, but instead as a particle. And we'll put the word photon on a little later, but these things are each called photons. All right, how did we transition from this concept to this concept? And by the way, it's not that we dumped wave. It's just that now it's both. Light has this wave-particle duality. All right, so let's get into what's with the particle part. So the best evidence that light actually acts like a particle comes from something called the photoelectric effect. And essentially, the photoelectric effect is based on the principle that high energy light can dislodge electrons from metals. All right, so scientists discovered a long time ago that if you hit a metal and you shine high energy light on the metal, electrons will actually leave the atoms of the metal and get dislodged, and they can just leave and become kind of free from the atoms. All right, how all of that happens and all that we can kind of put aside, but just for now, understand that they discovered this strange phenomenon that if you shine high energy light on the metal, you can kind of get the electrons to jump off the atoms. All right, now let's remember something about what we learned about waves. All right, what we learned, and we had this on the previous slide, is that high energy light can be accomplished really through two mechanisms. You can either have high amplitude waves, where you have, maybe your wavelength is long, but if your amplitude is really high, that should give you high energy waves. That's the concept here. Amplitude should be one way to get you high energy light. Or short wavelengths. That's another method of getting your light to be high energy. Maybe your amplitude stays small, but if you have very short wavelengths, you should also get high energy light. So this is fundamental to understanding the photoelectric effect, is that high energy should be able to be accomplished through amplitude being large or wavelength being small. And here's the main observation that leads to what we call the photoelectric effect, which leads to the concept of photons. Scientists discovered by a multitude of methods, when they shined the light on the metal, what they found was that the light, as long as the frequency, which as we know is related to wavelengths, as long as the frequency was large enough or the wavelength small enough, okay, you were able to shoot those electrons off the metal. All right, so in my picture, I've drawn kind of like a fairly small wavelength here. What they also discovered, and that wasn't a huge surprise because small wavelength should give you high energy. But what they also discovered is that if they took that same wavelength and they decreased the amplitude to very low, as long as they kept that wavelength the same, even though they made the light very dim, remember, low amplitude light is very dim. But as long as they kept the frequency of the light kind of reasonably high, or the wavelength reasonably small, remember those two are related. As your frequency is getting bigger, your wavelength always gets smaller. then you would still be able to dislodge the electrons. All right, so essentially, if you wanted to make a key point here, is that electrons were dislodged even by very dim light, as long as the frequency remained high. I'm oversimplifying a little bit. It had to reach a certain threshold, but as long as your frequency was relatively high, whether you were medium or very dim, your electrons still came out. And then in another set of experiments, when they're kind of playing with this a little bit more, let me make a little bit more room here. When the scientists shined light, and they're kind of toying with the light sources, they're kind of playing with the light that comes out of the light source. Scientists, if they increase the wavelength, which means lower the frequency, they were not able to get electrons to come out. Okay, so if they increase the wavelength, notice I increased the wavelength compared to over here. And that's not a huge surprise because they said, well, of course, you know, that kind of makes sense because we've increased the wavelength, that lowered the energy too much. But here's the major here's the major finding here. What they tried to do is they tried to say, well, maybe we sacrificed energy in terms of wavelength, but maybe we can overcome it with amplitude. So let's make the light, maybe the wavelength will still be long or the frequency small, but let's kill it with amplitude. This surely should be high energy light. Look how high the amplitude is. Look how large the amplitude is. And once again, no electrons were dislodged. So if you wanted to make a key point over here, is that even very high amplitude light was not able to dislodge electrons if the frequency was too low. And that's what's called the photoelectric effect. What has happened with the photoelectric effect? The major finding with the photoelectric effect is that this concept didn't seem to be true anymore. This was kind of violated because we weren't able to accomplish high energy behavior with amplitude. Only wavelength and frequency, because those are related. Only wavelength or frequency mattered in terms of being able to dislodge that electron. So if we were to make a major point to the whole photoelectric effect, is that only frequency, but not amplitude, was influential on energy. And that was why it was very puzzling to scientists, and that's why it took Albert Einstein to come up with a solution. It doesn't make sense, but Einstein was able to come up with a very simple, actually, but in some ways very genius solution. So let's talk about what Einstein's thought process was, and it's understandable enough for us to get it. So let's kind of reuse a little bit of our drawing. All right, actually I should leave that and get rid of this. So I'm going to reuse this drawing. So we have these two observations, but now let's basically come up with, and we can label this next part, the solution, Einstein's solution. He's trying to explain this phenomenon, and that is what I'm going to be drawing here. What was his solution to this bizarre decoupling of amplitude and wavelength or frequency? All right, so what Einstein proposed was that instead of thinking about light like a wave, Einstein says we're thinking of it wrong, at least in this context. Light is acting as a particle. Okay, so essentially here, when we are shining the light on this metal here, we should be thinking about the light that's coming out as a series of individual light particles, which we call photons. Each one of those is a separate photon. Picture just like a bullet shooting out of a gun, or, just individual ping pong balls coming out of some kind of a source. Each one of them is distinct, not connected to each other, and we call them each a photon. And what Einstein discovered, or his equation here, is that the energy of the photon is equal to what we call Planck's constant, which was obviously related to Max Planck's discovery, but just for now, understand that H is called Planck's constant times frequency. So go ahead and box this. This is an equation we're going to be using. The energy of each photon is equal to a constant. Let me give you what this number is. It's 6.626 times 10 to the negative 34th joules times seconds. Joules times seconds. And this is what's called Planck's constant. It's always the same number. So, and here's the issue here. Do you notice that the energy of the photon is not related at all to amplitude? Because there is no amplitude when it comes to a particle. That's only a wave concept. Notice the energy of the photon is only related to frequency, which is consistent with the discovery, the observations in the photoelectric effect. Only frequency mattered. And so that is what Einstein is proposing. So what he's saying is that the reason that you are able to dislodge electrons under these circumstances was that these photons had what was called the minimum frequency. In other words, it was high enough. It was a high enough frequency. It was a threshold frequency, as sometimes it's called. And that's why you were able to dislodge electrons. So let's come over here and talk about this side, because this side will bring it full circle here. So you've got minimum frequency. When we look at this scenario where we weren't able to get electrons, it was just that these photons had a frequency that was not high enough, or that was too low. And that's why you were not able to dislodge electrons, because each one of them had a frequency that was just too low. And here's the big thing here. Remember when I drew that huge high amplitude? Really, that was just very intense, very bright light. The concept here is this: with photons, very bright light is just more of them. That's all that is. This would be dim. This would be intense. And the concept here is that you still, even if you had very intense light, each of these just still had a frequency that was too low. It was too small of a number, so they didn't have enough energy in each one to pop out those electrons. Just to kind of give a very regular analogy to it. The concept, think about hunting, okay? If you are trying to hunt deer, if you hit a deer with one bullet, if it comes in with enough energy, okay, even one of them, it will kill the deer. It will pack the punch necessary. But the concept here is that if you're hitting a deer with ping pong balls, whether you have dim light, which is just a few ping pong balls, or hit them with thousands of ping pong balls, not a single one of them has enough energy, because the energy is just related to the frequency, not anything about intensity. And therefore, you're not going to kill the deer, dislodge the electrons. So I'm just trying to give like kind of a little analogy. This observation is really what leads to us accepting the idea that sometimes light is best described as a particle, where its energy of each photon is only related to this concept of frequency. And there's no such relation, no effect of amplitude or brightness on the energy of any individual photon. Okay, so with the photoelectric effect, we just Now accept that under some circumstances, like these experiments, light is best described as a particle. All right, now this equation is something that we will be doing some work with, some math with. So let's put up some practice questions. I'll do one that I'll just make up, and then I'll do another one from the book with you. So let's go ahead and say, I'm going to go to my electromagnetic spectrum page. Here, we talked about this last time, electromagnetic spectrum, and we're going to just make up a question, okay? So let's see, can we calculate the energy of a photon of, let me kind of move away from visible light. Let me do infrared light. Of infrared light that has a wavelength of, and notice I'm using that Greek letter lambda for the wavelength, a wavelength of, let's go, 1125 nanometers. Okay. So calculate the energy of a photon. So as soon as you see energy of a photon, and that's what you're trying to calculate, you know that this is your equation. The energy of a photon is equal to Planck's constant times frequency. Okay, now in the question, I've not given you frequency. I've given you wavelength, and that's very common. The concept here is that in this, whenever you have wavelength, you can get frequency. Very, very simple. You just have to recall another equation that related the two from the last slide, and that was C equals lambda times frequency. All right, so we're going to solve for frequency because we have lambda. We have wavelength. So frequency is C over lambda. We did this last time, so I'll move through it pretty quick. 3 times 10 to the 8th meters per second is the speed of light. We need that, oops. I've got my calculator in the other room. Go ahead and convert the 1125 nanometers to meters, because we need that unit to cancel, and I'll be right back. Alrighty, 1.125 times 10 to the negative 6 meters is the wavelength in meters. We need that to be in meters so that that will cancel. Now we put these two together. And we get a frequency equal to 2.67 times 10 to the 14th seconds to the minus 1, which is the same thing as a hertz, but we'll leave it as that. And then to get the energy of a photon, we simply multiply that frequency times Planck's constant. And hopefully you wrote it down in your notes. I won't put it up again, but it's always the same number. 6.626 times 10 to the negative 34th. Make sure you do negative 34th. Joules times seconds. And that will give us the energy of a photon equal to 1.77 times, actually, you know what? 4 sig figs, and Planck's constant had 4, so let me go ahead and be good here. So 1.767 times 10 to the negative 19th, and what would the unit be? Planck's constant had joules times seconds as a unit. Frequency is s to the minus 1. These two will cancel. Because remember, this one really is on the bottom, this is on the top, so they cancel. And so the unit is joules, which makes perfect sense. That's the energy of a photon. So that would be the answer to this question here. And it's small. I mean, you're talking about literally 1 photon. Okay, 1 photon. That's how much energy would be in 1 photon of this infrared light. Now, let's go ahead and do a slightly harder question. And I'm going to choose one from your textbook. So I might even have you just, let me see. I'm going to choose the one that's called, it's on page 307. Let's see here. Yeah, let me go ahead and I'll do the for practice 7.2. It's on page, I think I just said that, it's on page 307. So I'll do the for practice 7.2. All right, so it says a 100-watt light bulb radiates energy at a rate of 100 joules per second. So let's write that down here. A 100-watt light bulb, something very familiar, 100-watt light bulb, radiates energy at a rate of 100 joules per second. What they don't, well, I think they tell you in the next sentence. 1 watt is actually equal to 1 joule per second. These are interchangeable units. All right, watt and joule per second are integral. It's basically telling you how fast, how much energy per unit time you're actually emitting from a light source. All right, so therefore, we can replace the word watt, we can replace the W with joules per second. So if it's 100 watts, it's 100 joules per second. All right, that's what I can gather from that first sentence there. If all of the light emitted has a wavelength of 525 nanometers, so the wavelength of the light is 525 nanometers. Notice, even though we're thinking about photons, because even in the rest of the question you can see it's talking about photons, we still can measure their wavelength. I know that's a little bit confusing, but we just have to accept it as part of the wave-particle duality of light. We can still measure their wavelength. We just are going to have to turn it into frequency in order to use the energy of a photon equation. All right, if all the light emitted has a wavelength of 525 nanometers, how many photons are emitted per second? All right, so how many photons are emitted per second? Well, if we have wavelengths, pretty much guaranteed, you are going to have to turn that into frequency, because the two equations that we're going to use are this one. We're going to find the frequency, which I'll just rearrange it. Frequency is going to be and we just did one just like this, so that'll go really fast. And then after we do that, we can get the energy of a photon by Planck's constant times frequency. So it's really just these two very simple equations. So I'm going to not write so much on the board. Let me go ahead and find the frequency first. Turning 525 nanometers into meters. And then dividing the speed of light times that wavelength in meters. And I'm getting a frequency equal to 5.714 times 10 to the 14th, s to the minus 1. And now I'm going to calculate the energy of a photon with that frequency by timesing it by Planck's constant. And the energy that I'm getting is 3.786 times 10 to the negative 19th joules. I know I did that kind of fast, but you could pause the video if you want to do it a little bit slower. All right, that's the energy in one photon, the energy of a photon. All right, how are we going to finish the rest of this question? When you have a question that's dealing with multiple photons, like this one is talking, even the question it says, how many photons are emitted per second? Once you find the energy of one photon, one of the things that I like to do is just write a little conversion factor that is true about what I just discovered. There are 3.786 times 10 to the negative 19th joules per photon. Isn't that true? When I discovered that that's the energy of one photon, I can write a conversion factor, 3.786 times 10 to the 19th joules per photon. Just basically just saying something that's true. And now, all of a sudden, maybe you can see that the last step of this question is really simple. I was asking the question, how many photons are emitted per second? If I take this conversion factor and just use it upside down with the original number, 3.786 times 10 to the negative 19th joules per photon. See, these conversion factors are just so awesome. Now I'm getting the number of photons per second. You see how that works? So I just do 100 divided by that number, and I'm getting 2.64. Let me see how many sig figs I want. This one had 3, so I'm going to go just with 3. 2.64 times 10 to the 20 photons per second. And that should be the right answer. I'm going to bank that it is. I'm not even going to look it up, but these answers are all in the back of the book in one of the appendices. All right, so a question like this is a little bit harder, a little bit of an extension on the equations, but be ready to do something like this on the exam. Okay, now moving along. I'm probably going to go through these next parts a little bit faster than usual just because I don't have slides, nor do I have a colored printer. So it's just not as efficient of a way to teach this, but I'm going to do my very best. The next topic that we want to talk about is called atomic spectroscopy. Atomic spectroscopy. And this is, let me put this down for a second. This is the science behind things that you're familiar with. It's really the science behind fireworks. It's the science behind neon signs. If you've done these, you might know what I'm talking about. It's the science behind flame tests, which is a kind of a common lab technique for chemistry. But certainly fireworks and neon signs everybody's familiar with. There is a science behind all of this, and this is really called atomic spectroscopy. Let me show you a couple pictures. In the things that I don't want you to miss. These pictures are invaluable as you're doing your readings. These are glass tubes full of various different types of gases. In the first one, it's mercury. Second is helium. Third is hydrogen. And the reason that they're glowing is because they're plugged into electricity. All right, so that is just an observation. Scientists have discovered that if you expose atoms to energy via electricity or heat or a flame, you will see colors come out of the various different types of atoms, and each type of atom or each element will have a unique color. So mercury will always come out this kind of bluish tealish green, and these two will always come out their characteristic colors. So let me give you something to write on the board. Atomic spectroscopy, let's give you a couple bullet points, is that when atoms are exposed to energy in the form of electricity, which by the way is what you would get with neon signs, heat or flame, which is what you're going to get with fireworks. Okay, when you shoot energy in these various different forms into atoms, they will absorb the energy, they'll take it in, but then immediately, it's instantaneous, it happens like boom, immediately emit that energy, so it comes in and then it comes back out. What goes up must come down. Emit that energy in the form of visible light, and really a characteristic color. Each element will have a different color. I'm not going to write that part, but each type of atom will have a different color. Now, what's really neat about this is that if you look at it just with the naked eye, you'll see, okay, 3 different colors, that's fine. If you, let me show you this, I don't want you to miss these really important pictures here. If you take that light, this one here is the hydrogen lamp. If you take that light and pass it through a prism, which separates all of the individual wavelengths that come out, what you see is you don't get like a smear of colors. You don't get like, you know, all the reds, all the orange, all the yellows. You actually get very distinct wavelengths that come out for hydrogen. And for instance, if you do helium and you check out what comes out of helium, these little lines are very distinct wavelengths or frequencies that are coming out of the atom. You do not get a smear of all the different continuous colors that come out. It's very distinct ones. What you're looking at here are called emission spectrum or spectra, emission spectra for different elements. All right, so let me go ahead and say, put that bullet point. Very distinct wavelengths are emitted from the atoms. And that is what we call an emission spectrum. And that each emission spectrum is unique to each element. So really, this can act like a fingerprint. If you don't know what type of element you have in a sample, technically, you could do atomic spectroscopy on it, use these techniques, find out what its emission spectrum looks like, and then match it to the known ones and see, oh, that's barium. Oh, I must be dealing with barium. It's like a fingerprint. Each element has a very unique set of colors that come out. All right, so much prettier pictures in the book than what I have here on the board. But that's the observation of atomic spectroscopy, that you get these very distinct wavelengths that come out. You don't get a bunch of different a bunch of continuous wavelengths. You get very distinct colors. Now, how is this important? Atomic spectroscopy, there was a scientist called Niels Bohr. Niels Bohr. Bohr attempted to explain this phenomenon. And he did a really good job. And this led to what's called the Bohr model of the atom. Now, I introduced this last time in the previous video. The Bohr model of the atom is a very useful model of the atom. It actually does explain this phenomenon of these very distinct colors. However, it is not our current model of the atom. So everything that I'm teaching you here, you have to accept it from the point of view, a little bit of history. This is what people believe for a long time, but it was replaced with what we call the quantum mechanical model. But let's go ahead and talk about the Bohr model because it is a useful model and it does explain several different observations about the atom. All right, so what is the Bohr model? Let's go ahead and get something for your notes here. The Bohr model of the atom. A mental picture popularized or, not discovered, but it was his idea to come up with this model. All right, so when you draw the Bohr model, most of the time I'll draw it just like your book does. It almost has you drawing like a cross section, like the top half of a model. And I'm just going to do it or of an atom is what I should say. So picture you have a spherical atom, cut it in half, and we're drawing the top hemisphere of the atom on the board, which means that this part down here is the nucleus. And that's important that you always remember that even if we're discussing electrons and electron clouds and all of that, don't ever forget there's a nucleus in that atom, and that nucleus contains protons and neutrons. Unless you're hydrogen, you're not going to really have a neutron, but almost every other atom has neutrons. But at the end of the day, what's really important is that you remember your nucleus will be positively charged because of the presence of the protons. I got fuzzy. Let me see if I'll come back here. Because of the presence of the protons. So I always like to do it one positive just to remember that that nucleus is positive. In the Bohr model of the atom, what we have are these things called, well, they look like planetary orbits. But let me go ahead and label this one n equals 1. Let me do a couple more. N equals 2. And I'll explain this in just a second. What I'm trying to do is make these be closer and closer together as I go out, because that is actually part of the Bohr model. This would be n equals 3. Notice like an onion, Okay, the layers are getting closer and closer together as they go out. And let me do another one here. And this one would be n equals 4. And technically, we can keep going to infinity. Okay, but we'll stop with n equals 4. So this is how Niels Bohr attempted to explain what atoms look like on the inside. He wants to get some model. It's the best that he could do. So we got our nucleus. Okay, now let's talk about electrons. All right, so remember, he is trying to explain atomic spectroscopy. This is all trying to explain this phenomenon here. Why is it, whoops, where are we? Why is it that when we expose hydrogen atoms to energy, okay, in this case, the form of electricity, why do they always take in that energy, but always re-emit it as a color? That's the key concept here. And not only why is a color as visible light, no matter how the energy came in, it always comes out as visible light, but why distinct colors? And why are they unique to hydrogen and different colors for helium and different colors for barium? That's what he's trying to explain with this. So this is the concept here. In the Bohr model, let me go ahead and draw an electron here. This is an electron. In the Bohr model, electrons live in what we call stationary states. Stationary states, which are these kind of orbits that I'm drawing, each with a distinct n value. Okay, so the n value is just basically the first level, the second level, the third level, the fourth level. So stationary states, basically, stationary means you can't move. The idea here is that the electron cannot live anywhere. It can't live in between. Okay, this is not allowed. The electron cannot live in between. It must live on one of these stationary states. And electrons can transition. Now they have to do it instantaneously. Between stationary states. If a photon is absorbed or emitted. Okay, let's stay on this for a little bit here. An electron can, now it's got to live in one of the stationary states, but it can transition to a new stationary state. However, that has to happen instantaneously because it can't live in the middle. So it doesn't travel and spend any time at all between the stationary states. It's like, they're called quantum leaps. It's either here, here, and it can transition. Why would it transition? Here's the atomic spectroscopy part. If you have let me draw one other thing here. As the electron moves farther away from the nucleus, it is increasing in energy. E, that's an E. Because understand, electrons are negative. They want to be close to the nucleus. So they're more stable near the nucleus. If you move them away from the nucleus, they increase in energy. Okay, if you have a photon absorbed, so this is where you're plugging that neon sign into the outlet, you're exploding a firework, you have energy coming in. If you have a photon absorbed, so let me do a little photon of light coming in here. If the photon of light, let me just make this the photon, comes in, it will cause the electron to jump up to a higher level. Now, in my picture, I'm just going to have it jump up 3 levels because it makes it go higher in energy. That photon comes in, it makes the electron jump up. Now, just like if I throw my marker up in the air, what goes up must come down. As soon as that electron jumps up, literally instantaneously, it will fall back down, okay? Sometimes to different levels, but let's just say it falls right back down. So this is the absorption of a photon that will make it jump up. The photon comes in, it jumps up. Then when it falls back down, this is the emission of a photon. And how does that photon come out? It always comes out as a photon of visible light, a color. Roy G. Biv, one of those colors comes out. So that's the concept here, is that you get the photons coming in, making it jump up, but then when it falls back down, the photon comes out, but it always comes out as one of those visible light colors. Now, this picture here is explaining, it's connecting the Bohr model to atomic spectroscopy, the emission spectrum. When you have that fall back down, if you fall multiple levels, so this one here, this electron falls from 5 to 4 to 3 to 2. This fell 3 levels. That's a very high energy fall. Picture falling off the Empire State Building. You're going to get a high energy photon coming out of that atom from that fall. And that will give you violet light, which frankly is the highest energy type of visible light. It's the shortest wavelength. However, if you have a fall from this one here, n equals 3 to n equals 2, this is a small energy fall because picture falling off a shed. You're not going to fall that hard. So when that photon is emitted, you're going to have a fairly low energy form color come out, red. Remember, red is the lowest energy form of visible light or the longest wavelength. And why do we get all these unique colors or these different wavelengths for different atoms? It's because each atom has a unique profile of protons and electrons. Even different numbers of protons and electrons. And what we're going to find out later is different, occupying different orbitals and things. So the electrostatic forces in every type of element is different. So you're going to get different distances of falls, which will give you different colors coming out. That is the concept of atomic spectroscopy, and that is the explanation of the Bohr model. So let me tell you what, well, there's a lot of good things about the Bohr model, but what we do know now here is that electrons don't live in these orbits. Okay, it's not like planetary orbits. You can see why Niels Bohr thought so, because we can see the, we know about the planets and the sun. So you think maybe in nature certain patterns are repeated. But what we know is that electrons don't live in orbits. They live in orbitals. Orbitals are 3D zones. Okay, so that's what we're going to transition into learning about in just a second. However, the Bohr model is useful for explaining atomic spectroscopy. I do want to give you one more equation that is used in conjunction with atomic spectroscopy and electron transitions. And that is this equation here. It's in your textbook. But the energy of the photon, I'm going to actually change it just slightly. I think yours says delta E, but I'm just going to go straight to thinking about just the photon. The energy of the photon that is either coming in to jump you up or coming out with the fall is equal to negative 2.18 times 10 to the negative 18th joules times 1 over n final squared minus 1 over n initial squared. Okay, so go ahead and jot this equation down. Make sure I have my numbers right here. I think that I do. But you can calculate, the energy of the photon that comes in or out based on what n levels you fall from and to. Let's go ahead and just do a practice question on this here. And actually, let me grab one because this is not the type of thing. Oh, actually, I can just make one up. Can you calculate the energy of the photon that is released? Or let me say emitted. When an electron falls from n equals 4 to n equals 2. And actually, let me have you do another question here. What color is that photon? I'm making this up on the fly, but I think I can do it. All right, so we have an electron falling from 4 to 2. So in the picture, this is a fall, so 4 to 2. You're losing energy. The electron is going to lose energy. So that's why I said the photon is emitted. Anytime the electron goes from high to low, you're going to have that photon come out. The photon comes in when you push the electron up, but when the electron falls, the photon comes out. That's why I chose the word emitted and when the electron falls. So let's go ahead. I'm going to erase my Bohr model. Let's go ahead and see if we can calculate this. Oh, and by the way, I'm kind of leaving out this detail, but this is always from a hydrogen atom. Once you have multiple electrons, things get more dicey. So this is a hydrogen atom, but let's just kind of go ahead and assume that. Okay, so energy of the photon is equal to this number here, negative 2.18 times 10 to the negative 18th joules. Pretty simple equation, times 1 over n squared final. So of the two, which one is these is final? This one is your final n. That's your initial n, because it fell from this to that. So final is 2, but we're squaring it, so that becomes 4. And we're going to subtract 1 over n squared initial. So 4 squared is 16. And that is all you have to do. I usually find this number first, so we want to do 1/4 minus 1/16. And then we're going to times whatever number you get times this here, times negative 2.18 times 10 to the negative 18th. And I'm getting the energy of the photon is negative 4.0875 times 10 to the negative 19th joules. Okay, so that is, now here's the thing. The negative is just there to really tell you that the photon is coming out of the atom or emitted. It's kind of like thermochemistry. It's just telling you the direction. Just like if you have a negative Q, it just means that amount of heat is coming out. The magnitude of the energy is the absolute value, the 4.0875 times 10 to the negative 19th. This is just consistent with the fact that that photon came out. That's why it was negative. What you'll find if you have a jump from low to high, you'll get a negative number here that ends up timesing by a negative there. And that means you're going to get a positive answer, which means the photon comes in. All right, so that is the answer, 4.0875. That's the energy of the photon. Whether you have the negative or not in there, it doesn't matter to me because I know what it means. Now, what color is that photon? Understand, color is related to wavelength. Now, if we can remember that the energy of a photon is equal to Planck's constant times frequency, that if we divide both sides by Planck's constant, we'll get frequency. So let's take the energy of that photon. Now I'm going to take the absolute value. I'm going to lose the fact that it's a negative. I understand that it's coming out, but I'm just going to use the positive number. So let me make that positive. And now I'm going to divide it by Planck's constant. Once again, Planck's constant being 6.626 times 10 to the negative 34. And I'm getting a frequency equal to 6.168 times 10 to the 14th s to the minus 1. And now I'm trying to get what color it is. Color is wavelength. So back to this guy here. Anytime I know frequency, I can get wavelength. It's very simple. Just divide speed of light by frequency. So now I'm doing the speed of light, 3.0 times 10 to the 8th meters per second, and I'm dividing by that answer that I just got for frequency, and I'm going to get the wavelength. Let's see here. 3.0 times 10 to the 8th. Oops. And I'm dividing it by the frequency. And I'm getting a wavelength equal to 4.86 times 10 to the negative 7th meters. Remember, that's going to be meters because speed of light was meters per second. and I'm dividing it by s to the minus 1. These two will cancel because they're both in the denominator, and your answer will be in meters. Now, to give meaning to it, let me put that into nanometers. So I'm going to times it by 10 to the 9th. And I am getting 486 nanometers. Now, I don't know what color that is. However, we have a chart that will tell you what color it is. So if you look at if your electromagnetic spectrum page, isn't this cool? 486 nanometers is between 450 and 500. Whoops, hold this straight here. And that, I guess you could call blue. It's blue, somewhere in there. It's going to be a blue photon. So all of this is very law-driven. It's very equation-driven. You can calculate all of these things. Now, we need to speed along. I'm going to have to skip through quite a bit if I'm going to get to my quantum numbers. So I do want you to do the readings. And let me just, I won't even write everything on the board, but let me just go ahead and mention that all of this leads us to something very important, a very key point. Actually, let me write just a little bit. The key point of the quantum mechanical model. So once again, the Bohr model ends up getting replaced by the quantum mechanical model. This is our current model of the atom. The whole crux of it is that just like light, let me write this down. Just like light, electrons have both a particle and a wave nature. When that was discovered, that they have both a particle and a wave nature, the electrons, these negatively charged things we've been talking about all semester, that changed everything. Let's stay on this just for a little bit. The particle nature we already knew. This was no surprise, because just think about it. They have mass. We started out early in the semester talking about the mass of electron. It's very small. I think it was 0.00055 atomic mass units, very much smaller than a proton. But they have a mass, and if you have a mass and you take up space, I'm just my little electron, you're a particle. And that's what everybody has just understood. What in the world is with the wave nature? The wave nature of an electron was, I don't know how to pronounce his name, so I'm not even going to try, but was discovered through a couple of very amazing experiments. And let me go ahead and show you really the key here, because this is just so cool. I can't not show you. This picture here, this is figure 7.16. Okay. This is so cool, especially since we've talked about the interference pattern before. We're going to start at the bottom. At the bottom. Okay. So I'm going to just butcher his name, but de Broglie. Okay. What he did is he has a barrier, a wall with two slits. Doesn't that sound familiar? Sure sounds like the light experiment that we had discussed in the last video, and it's exactly similar. So you've got a barrier with two slits. And what de Broglie aims not at the barrier is electrons, an electron beam, not light like the previous experiments that we looked at, but an electron beam, likely from something that was emitting radioactivity. So he's aiming it at the aiming the electrons at this barrier. Now, what he expected, if you look here, this says expected behavior for particles, was that just like any particles, the ones that hit the wall, picture shooting a bunch of ping pong balls at a wall with holes in it. The ones that hit the wall are going to fall right back. That's just common sense for any kind of particle. And then the ones that happen to be lucky enough to hit where the slits are will just go through, but they'll follow a trajectory. And so you'll end up seeing on a film on the other side, lines that match the spacing of the slits. So let me put this down for a minute here. You have a barrier. You have two lines in it. Picture taking a gun, anything that shoots particles. If you hit the barrier, they fall right back. If you happen to hit where the slits are, they keep going through and they hit the other side. That was what de Broglie expected the electrons to do and to make film have this pattern on the film. Instead, look what he saw when he did these experiments. Black, white, black, white, black, white. And all that we really need to take from this is that that is an interference pattern. And we spent a lot of time in the last video making the point that the only explanation that we have for interference patterns, black, white, black, white, black, white, is wave nature. Diffraction with subsequent interference. That's the only explanation we have. So from there, it was concluded that electrons have a wave nature. This is the key experiment, oh, this one here, that you get an interference pattern when you aim an electron source through two slits. Very cool. Now, showing you another slide here. This gets a little bit tricky, but it's really neat, so we want to at least try to appreciate it here. When they did the same experiment, but they put a laser beam in back of the slits to try to detect where the electrons were. Picture, I think the laser would light up wherever the electrons went. When they did that, in order to try to detect, okay, it's going through this hole first, then it's going through this hole next, to try to detect where the electrons were passing through at any one moment, what happened was really bizarre. The electrons stopped doing the interference pattern, and they went back to just a particle nature. So when they tried to basically locate the position of the electrons to either this hole or this hole, they stopped behaving like they had before. That leads to something called the uncertainty principle, and this is very physicsy, but the idea here is that electrons never act as both a particle and a wave at the same time. They do one or the other, but never both at the same time. The implication of that, and I'm not going to spend much on it, and I'm not even going to put much on the board, is that because the particle nature is related to its position in the atom, because particles can be positioned, okay? They can have a longitude and a latitude. Okay, so actually let me just write this here. The particle nature is related to position. You can position a particle in the universe, whereas the wave nature, you can't position a wave. It doesn't have a unique, distinct spot in the universe. The wave nature instead is related to velocity, where it's going, where it's headed. All right, and I'm skipping some stuff, so just kind of accept this for now here. Because you can never observe both natures at the same time, you can never know both position and velocity of an electron at the same time. We can never know an electron's position and velocity at the same time. This is what's called the uncertainty principle, or at least it's a form of it. But what it does lead us to is this major concept about quantum mechanical theory. Therefore, we can only calculate, that says calculate, probabilities of where an electron in an atom is most likely to be. Wow, I ran out of room. But that says, because we can't ever see the particle and wave nature at the same time, then we can never know an electron's position and velocity at the same time. Which means, instead of knowing exactly where it is, because as soon as you know where it is, you don't know where it's gone. What we can only do is calculate what are called probabilities of where an electron in an atom is likely to be. Now, the good news about this is that you're not doing any of these calculations. I'm not doing any of these calculations. The only thing that you have to accept is that everything about quantum mechanics is just based on where we think the electrons are. There's no guarantee they're in any one spot in the atom. And so who did all these calculations? And now we're getting into the last part here, which is the quantum numbers. A man named Schrödinger. Brilliant, brilliant. Actually, all of these people were beyond brilliant. Schrödinger did the probability calculations. So he's like the mathematician, okay? Probability is a math concept. Schrödinger did the probability calculations about where in an atom electrons could be, okay? And these are what we call orbitals. Oh, let me say this. His solutions to his equations. So he did all these very, very complex equations lead to the orbitals, okay? So very difficult equations. When he solved the equations, he actually gets what are called quantum numbers, and we're going to put the quantum numbers on the board. But the quantum numbers define what are called orbitals. Orbitals are really not anything. All that they are like zones where electrons can live. And actually what they are, they're three-dimensional. They're not like orbits in the sun. They're three-dimensional zones where electrons can live, but they're really just probability. They're called probability distribution maps. When you look at a picture, let me show you just what one looks like. This here is what we describe is one type of orbital. And what you'll see is a bunch of like pixelated blue spots. These are just mathematical probabilities of where an electron can live in this one particular orbital. At the end of the day, it's important for you to understand they're just zones. Orbitals are not, they have no membranes. They're not contained. They're just spaces in an atom where an electron can live. If you know anything about basketball, there's something called zone defense. It's not it's an area, okay? And that's kind of the same type of thing about orbitals. They're 3D zones where electrons can live in an atom. Where do they come from? They come from the solutions, the mathematical solutions to Schrödinger's equations. We're not attempting to do any of his equations. All that we want to do is talk about what his solutions were, which are called quantum numbers. And this is going to lead us to finish this up. Probably go about 15 more minutes and then we'll be done. Let me go ahead. Actually, yeah, let me go ahead and get a fresh black marker here. We are going to be learning about the quantum numbers. Quantum numbers. And once again, the quantum numbers are simply the solutions to Schrödinger's equations. That's what they are. Like the answers. They lead us to what are called quantum numbers. Now, let me intro this with this. There are 4 of them. There are 4 quantum numbers. They're N, L, ML, and MS. And I'll define each one on the board. However, let me preface it with this. 3 of them, these 3, describe orbitals. Those zones in an atom where an electron can live. The 4th one's a little different. This one describes the electrons in the orbitals. So of the 4, he's a little different. This one focuses on telling you something about the electrons. It's going to end up telling you about the electron spin, but I'm going to wait until the next chapter to really get into MS. I'm going to focus on the board here on the first 3 quantum numbers, N, L, and ML. These are the ones that define or describe the types of orbitals that an atom can have based on Schrödinger's probability equations. All right, now let's go ahead and divide our board into 3 sections. The first section can be, the first and the fourth can be kind of small. The middle one, I think, is going to take the most space. So I'll do it like that. All right, these are going to be our 3 quantum numbers. So let's go ahead and start with the first quantum number. You need to pretty much know everything about the quantum numbers. Everything that goes on the board is important. So the first one is called the principal quantum number, Qn. Principal quantum number. And he is the one that we use when we use the letter N. And by the way, this is in a way similar to the Bohr model, this part. Remember there were N values? That kind of got perpetuated with quantum mechanics. So the principal quantum number N. Now with all of these, let me make a title here. With all of these, Schrodinger's equations lead to what are called possible values. Just like in math, kind of like, you know how you're not allowed to divide by a 0? It's like impossible. There are certain possible values for all of his equations. And like I said, the equations are so complex we don't try to understand them. Just, at least in this course, just understand that there are certain allowable values mathematically for all of the quantum numbers. And you have to know what the possible values are. So the possible values for N is that N can be 1, 2, 3, etc. And it can go to infinity. But essentially what I'm saying is that N cannot be 0. And it must be a integer, a positive integer. A positive integer, a positive whole number. So 1, 2, 3, etc. are the values that N can be. So you can have orbitals that have an N equals 1. You can have orbitals that can have N equals 2. You can never have orbitals that have an N equals 0. All right, now, in addition to possible values, let's go ahead and talk about what does N tell us. So basically, let me go ahead and write the word significance. What is the significance of the N value? What is it telling you? N describes 2 things, the size, but also the energy of the orbital. And essentially, as N increases, size and energy also increase. So I'm just doing S and E. You could write size and energy increase. So as your N values are getting, going from 1 to 2, your orbital is actually getting bigger. So N equals 1 would be the size, N equals 2 would be bigger, N equals 3 would be even bigger. Now, size is kind of obvious. Why energy as well? Well, remember, inside the atom is the nucleus. So the farther you move away from the nucleus, the higher in energy your electrons that are living in that orbital, they're going to be higher in energy because they're farther away from where they want to be, which is near that nucleus. That's also consistent with what I had on the board for the Bohr model. So N describes size and energy. As N gets bigger, size and energy gets larger, and the possible values. That's called the principal quantum number. Now, the next quantum number is called the angular momentum quantum number. And the angular momentum quantum number is abbreviated with the letter L. I read it in cursive just so it doesn't look like a number 1. Let's talk about possible values. So, according to Schrodinger's equations, the possible values for L actually depend on N. So let me write the word depend on N. It depends on what your N value is for the orbital as to what your L values can be. That's why he's called the principal quantum number. He's like the head of the school, the principal. He kind of affects what you can do down the line. Okay, that's why he's called the principal quantum number. So the possible values for L is this. L can be all whole numbers from 0 to N minus 1. And so that's the rule that you want to get. L can be all whole numbers from 0 to N minus 1. So let's go ahead and lay this out here because it's kind of important. If N is equal to the very first number that N can be, which is a 1, if n is equal to 1, L can be what? Well, L can be all whole numbers from 0 to n minus 1. So put 1 in for n, and you still get 0, right? 1 minus 1 is 0. So really, L can only be a 0. But if n equals 2, L can be all whole numbers from 0 to 2 minus 1, which is 1. So therefore, if n is equal to 2, L can be both 0 and 1. Those are both possible values. If n is equal to 3, L can be 0. Well, just put a 3 in for there. 3 minus 1 is 2. So it can be 0, 1, and 2. You can, any number from 0 to n minus 1 is going to be allowed. And then if n is 4, hopefully you can see what the possibilities are. Any number from 0, or all numbers from 0 to 3. 4 minus 1 is 3. So 0, 1, 2, and 3. So we stop there because we might not know it yet, but these are the only L values that are used on the periodic table for all the elements we know. So I'm just going to stop with those ones here. So these are your possible values. Now, what is the significance of L? Of this L value? What is it telling you? This L describes the shape of the orbital. Like I said, they're not orbits, they're orbitals. And they can have various different shapes, shape of the orbital. They're not like planetary orbits around the sun. So if you've drawn atoms like that, it's the Bohr model. It's not the current model. It's not actually how we understand atoms today. So let's talk about the various shapes that orbitals can be. So L is telling you what shape it is. Now, a little chart is going to be important here. That's why I made this one a little bit bigger. Let me see if I can fit all of this in a little chart. Okay. What I want to have you do is list the L values. We got the ones that we have on the board are 0, 1, 2, and 3 are the possibles. 0, 1, 2, and 3 are the L values. And let's talk about what the shapes are of those various L values, because they all have a shape that's associated with that value. When L is equal to 0, we call these s orbitals. S orbitals. And s orbitals is a lowercase s. And s orbitals are shaped like a sphere. I'm just drawing a little spherical dotted line. Now 3D, not like a circle, it's a sphere. Where like the nucleus would be in the middle, but that's the orbital. It's dotted because I want you to make sure you understand. It's just a zone, okay? It's just an area, but it's spherical. So if you have an s orbital, you want to picture it as a sphere. When L is equal to 1, which is the quantum number that you're not going to have this shape if you're at n equals 1, but you will start getting this shape starting with n equals 2 when L is 1. So when L is 1, these are called p orbitals. P orbitals. P orbitals are shaped kind of like a bow tie. Now, I feel like that red is not showing up, so I think, let me go ahead and do it in black. Let me do this is the S, spherical. P orbitals, shaped like a bow tie. Now, this is a single orbital that I've drawn here. It's just one orbital. It looks like two, but it's one orbital. What you're looking at here, though, is that p orbitals have what are called two lobes. So that's a p orbital, but it has two lobes. That's one, that's the other. And it also has in the middle one node. A node is a place where the electrons cannot be. They cannot live in the node. By the way, that's where the nucleus is going to be. So it kind of makes sense. But that is where that's what a p orbital is shaped like. So two lobes, one node. Let me go ahead and clean this up a little bit so I can have room for my next type of orbital. When L is equal to 2. These are called d orbitals. D orbitals, lowercase. All of these are lowercase. S, P, and D, all lowercase. D orbitals are shaped like four-leaf clovers. You'll see nice pictures in your book, but it's shaped like a four-leaf clover. That is a single d orbital, but a d orbital has four lobes. Hopefully you can see. 1, 2, 3, 4. 4 lobes, L-O-B-E-S, but it has two nodes. I know it looks like only one, but it really is it's actually two. Two nodes in the middle is a d orbital. And the last type of orbital is an f orbital. And that's the type of orbitals, the shape that you get when L is equal to 3. And the only thing that I'm going to attempt to say about this shape is that it's complex. You'll see in your book, they do have some nice pictures, but we're not going to attempt to draw it. So the L value is significant because it describes the shape of the orbitals. If you have a different L value, you'll have a different type of shape. All right, moving on to the last one. The last one is called the magnetic quantum number. The magnetic quantum number. And this is the one that we abbreviate with M sub L, subscript of L. What is this quantum number all about? Let's start with possible values. Possible values. All right, so just like L depended on N, see how I wrote depend on N? The possible values for ML depend on L. So they all kind of depend on the previous quantum number, which is why he's called principal. So ML can be all whole numbers between negative L to positive L. Now, this is best explained using a number line. Okay, so if you have like a number line, or try to draw a number line, and you really only have to go up to 3, you'll see why in just a second. And let's make those positive. So draw yourself just a little number line here. It really does help for this. So let's talk about scenarios, okay? So if L is equal to, well, what was the first type of L value that was even possible? It was 0. These are S orbitals. If L is equal to 0, ML can be, well, all numbers between negative L and positive L. So negative 0 to positive 0, you're still just 0. So the ML value can just be a 0, and that's it. However, if L is equal to 1, which is the next number that L could have been, that was possible, then ML can be all whole numbers between negative 1 to positive 1, because L is 1. So it can be negative 1, 0, and positive 1. Negative 1, 0, and positive 1. So you just want to walk up the number line from the negative L to the positive L, and you could list all of those as possible values for ML. So with this one, you can get 3 possible values. When L is equal to 2, ML can be, L is equal to 2, so all numbers from negative 2 to positive 2. So negative 2, negative 1, 0, positive 1, positive 2. And that's all the numbers that ML can be in this scenario. So you can actually have 5 different, oh, that should be in parentheses, 5 different ML values when L is equal to 2. And then when L is equal to 3, ML can be all the numbers from negative L all the way up to positive L. So you just list them, negative 3, negative 2, negative 1, 0, positive 1, positive 2, positive 3. And that is where we stop because, like I said, on the modern periodic table, there are no L values bigger than 4. Or, sorry, bigger than 3. All right, now, what is the significance? I kind of ran out of room, so I am going to actually write it up here, but you could just write it below. We're almost done. What is the significance of this ML value? What is it telling us? ML describes the orientation of the orbital in space. If you are struggling with the concept of orientation, just think, what direction is it facing? All right, so let's talk about, so orientation is the kind of, how is it oriented? Is it facing, like right now I'm oriented towards the camera, now I'm oriented towards my door, now I'm oriented towards the board, direction. Okay, so let's talk about, let's come back here and just wrap this all up here. When L is equal to 0, let's just kind of put this all together because it makes perfect sense. And it really is important to understanding electron configurations. I'm going to have to erase a little bit to get myself a little bit of space. But hopefully in your notes you can make this a bit neater. I'm going to keep up this little chart here because I'm going to refer back to it. But I'm still talking about ML, so I just want to kind of give myself a little space on the board. Whoops. All right. When L is equal to 0, these are called s orbitals, correct? That's what L is equal to 0 means, s orbitals. What that means is that because there's only one value for ML, there's only one orientation. There's only, which actually makes perfect sense, because if you are a sphere, you can't really, you're just like a, picture a tennis ball. You can't orient it. It just is. If you try to turn it, as long as it doesn't have printing on it, it's just the same direction. It's just one orientation for a sphere. So there's only one orientation, and thus only one orbital. There's only one. When you're talking about s orbitals, there's only one of them, because you don't get multiple orientations. However, when L is equal to 1, which is what we call p orbitals, these are called p orbitals. When L was equal to 1, there were actually 3 different orientations that they came with. So there are 3 different orientations for these p orbitals. And what that means is that whenever you have p orbitals, you always have 3 of them oriented in different directions. You get one which is called the px orbital, which is oriented horizontally on the atom. You get another one which is oriented vertically on the atom. He's the py orbital. So they're the same shape, they're the same size, but it's a different orientation. It comes from the fact that there's 3 different ML values. And then you'll have a last one, this one being called the pz orbital. And this one is essentially coming, on the board you draw it kind of diagonal like this, but it really just means coming out at you as a z-axis, like coming towards you off the board. So the idea here is that when you have p orbitals, because your L value is 1, you don't just get one orbital. You actually get a set of 3, each of them oriented a different way in space. Let's see what happens with the other types of orbitals, the Ds and the Fs. When L is equal to 2, these are called d orbitals. How many of them will you have? Well, it's all defined by the quantum numbers from Schrodinger's equations. When L is 2, you actually have 5 different orientations. 1, 2, 3, 4, 5. 5 different quantum numbers is 5 different orientations. And essentially that means that you'll have 5 of these oriented in different directions. I'm going to kind of draw them like this. I mean, it's going to be hard for me to draw the different orientations, but you get 5 of them. That's what this picture is trying to show you. 5 of these clover leaves oriented in different directions on the around the center of the atom. So when you have d orbitals, it doesn't just come as 1. You get a set of 5, all facing different directions, declared by the number of magnetic quantum numbers. And then lastly, L equals 3. These are called f orbitals. These are the ones with a very complex shape when L equals 3. And how many will you get? 1, 2, 3, 4, 5, 6, 7. You will get 7 of them. So with d orbitals, you get 5 of them. With f orbitals, you get 7 of them. Now, that is the significant, or that is the quantum numbers, the three that describe orbitals. Let me just put this all together so that we can kind of move forward in the next video. We are going to be learning how to write what are called electron configurations, which basically tell you like what orbitals the electrons are in. And say if I describe an orbital, and I describe it as the 3py orbital. This is basically an orbital name. Okay, so scientists can say, I want to talk about the 3py orbital in an atom. Okay, what you're looking at here is all three quantum numbers. The 3 is the n value. That's the principal quantum number, and that tells you that he's in the level 3 in terms of size. So he's not the smallest orbital, not the second smallest. He's the third largest type of orbital. Third as far as away from the nucleus. So that's the principal quantum number. That's what that's telling you. The p is related to the L value. Remember, that's the one that's telling you the shape. Once again, p is equal to an L value of 1. And that's going to tell you what shape he is. And then this here is the ml value. And this is telling you what axis he lies on. How is he oriented in the atom? So if someone was to expect you to draw a 3py orbital, just to kind of get the sense of it, if you had to kind of picture it in your mind, because so much of chemistry is just thinking about it correctly. Here's my nucleus. Okay, I'm not going to draw it really small because it's in, you know, it's going to be actually bigger than what we call a 2p orbital. It's actually going to be bigger. But I have to draw it as a p shape, and I'm going to draw it on the y-axis. So it would be something like this. That would be the 3py. Whereas if I wanted to draw, this would be the 3py. Whereas if someone was to superimpose, okay, that's the 3py, what does the 2py look like? It would look like this. Same shape, same orientation, just a little bit smaller, and that's my nucleus right there. If someone was to ask me to draw the 1s orbital, okay, the 1s orbital, let me draw him in blue. Let me see if I can grab my blue marker. So I've got the 3py in black, the 2py in blue. Let me draw my 1s in green. Let me draw my 1s in blue. 1s would be spherical, and it would be smaller than both of these, so something like this. And when you put all of those orbitals together, you end with this very last picture. If you kind of superimpose all of them, that's really quantum mechanical model of an atom. It's all of these orbitals, these zones, and when you put all of them together, it's going to make the atom spherical. And this is all the different places electrons can live in an atom. And we are going to kind of move on to, in the next chapter, locating the electrons in an atom in what we call electron configurations and orbital diagrams. There's a lot of really cool stuff ahead. Even in the numbers that I was talking about, how you could have 1s orbital, you always get 3 p's, you always get 5 d's, you always get 7 f's. I'll kind of not give you the end of the story here, but even that pattern alone completely explains your periodic table. It's all one big, beautiful story. So there's a lot ahead that kind of is really interesting. So anyways, that was longer than I thought it would be, but we did get through all of chapter 7. And so thank you for your attention. And we will look forward to doing another video next week. Thank you.